Record. All right, so welcome back to Math 383 Complex Analysis. So this is going to be lecture 4. So you were supposed to have watched the video beforehand. I will be talking about the proof of Goursat's theorem. It looks like there's a couple of small typos in my handwritten lecture notes about that, but I think the video was actually correct. So I want to talk about the main ideas of that. I want to talk a little bit about convergence of series, a little bit about primitives. Is there anything else that people want to discuss? And again, in advance is always a little bit better, so I can try to structure the lecture. You are welcome to bring things up, right in class. I want to explore how to use class time more efficiently. Now that we have access to a Zoom mindset of just watching things. There's also the advantage of, if it's on YouTube, you can change the playback speed to 1.25, 1.5, 1.75. Depending on how far you can go. I'm sorry? You could do 0.5, yes. And then you would see just how ponderous of a subject this truly can be. All right, yes.
If we have time at the end, could we just sort of go over a few more examples of like complex functions and understanding?
Yes. And in fact, that's exactly the reason to be doing stuff like this, so that we have time to do stuff like that. All right. And I'll talk a little bit, if time permits, on why we care about stuff like this. Thank you. As to why we care about complex analysis. What kind of problems can it help us attack? And then if there's time, we'll talk about sniffing out equations. Did the video talk about the product rule and sniffing out the product rule? Okay, no. Okay, so then if time permits, I'll talk a little bit about that. Okay. So what I want to start off with is primitives. Can someone tell me what a primitive is in complex analysis? It's an antiderivative. And yet again, you will be left with the question, why are we introducing new terminology? That's above my pay grade. So f is a primitive for little f if big F prime equals little f. Sometimes I try to wear the same shirt I wore, the last time I taught the class, try to align the lectures with whatnot. I think it was a light blue shirt last time. There is a reason I'm wearing this beautiful shirt. Why did I write a primitive? It's not unique, right? What is the best school for college football? Other than Williams, of course. I'm sorry? I'm sorry? What is the name of the school? The Ohio State University. Not a Ohio State. So this is one of the big things in mathematics. You want to understand the difference between A and the. When you see the, you think that there's only one. This is a primitive. There is more than one. It is not unique. So it is unique up to a constant. And we've had some homework problems that discuss just how much can you specify a function. And for some things, we will actually find that if you specify the function on the boundary and it's complex differentiable, that actually gives you all the values inside as well. Physically, you could often view this as maybe I give you the distribution of heat on the boundary and then you'll figure out what the heat is inside. A lot of physical problems people try to model by saying, well, the mathematics then say that this must happen, therefore this must happen for the physical system. That only works if the physical system is actually described by the mathematics. And so you can never really prove that the mathematics describes the physical system. So you have to be a little bit careful with arguments like that. And so the idea is that if we have a primitive, then integration is going to be easy. Now, what kind of curves do we like to integrate over in complex analysis? Closed curves. We love closed curves. What is your favorite theorem from Calc 2? Well, the most important thing from Calc 2. The FTC, right? Friendly trade commerce. No, the fundamental theorem of calculus. Now, you normally do it as the integral from a to b of f of x dx equals big F of b minus big F of a. Let's do the special case of a closed curve. So what would the closed curve look like in the one-dimensional world? A point. So we would have the integral from a to a of f of x dx equals big F of a minus big F of a equals 0. This truly does not merit the name fundamental. And we have to remember that what we're doing here is this is the area under y equals f of x from x equals a to x equals b. If I don't use the word area, this is not the fundamental theorem of calculus, this is the fundamental definition of calculus. The content is that you can compute the area by knowing the antiderivative. If I don't say area, there is nothing to be excited about. Okay? Is anybody truly impressed that the integral from a to a of f of x dx is 0? Okay, we agree that this is really nothing. The generalizations, however, that's where the meat is. And that as you generalize, things become very interesting. If I want to walk from here to the door and I can only walk in a straight line, do you think I can do this? Okay. And if I have Superman or Supergirl standing in the way, do you think I will be able to walk past them? No. If I'm stuck in one dimension, there's nothing I can do. However, in 2 dimensions, I can easily walk and just detour and go around a circle. So you have more paths available in higher dimensions. And so you have the option of having interesting things happen. For my physicists, what is the most interesting classical force to look at?
Gravity.
Gravity. And what kind of force is gravity? What's the equation?
F equals mg, or there's
Well, that's the acceleration near the Earth's surface. And we don't want to just limit ourselves to the Earth. We want to consider the entire universe. So what would gravity be?
I mean, there's the gravitational constant.
Good. So it's G
G m1
m2
over r squared.
over r squared. So you have a force that is proportional to the product of the masses and inversely proportional to the square of the separation. The further you are, the weaker the force is. And the force blows up at the origin. So you actually have a singularity. So when we talk about working with functions that have singularities, this is not something where we can just sweep under the rug. When we're looking at physics, this was not a offensive question, right? We've never seen, well, I can't say we've never seen each other before. Not only have we been in week 2 or week 1, depending on how you count, but this is physics. 1 over r squared. We've got to deal with stuff like that. So having functions that blow up, we need to be able to handle stuff like that. And so the interesting thing will be, you could be doing work on the boundary where everything is well behaved, but because of the singularity at the origin, that's going to impact how things are everywhere. All right, so we agree that if f is a primitive of little f, we have a very nice way to do the integration. It turns out in complex analysis that this generalizes. So we can generalize the fundamental theorem of calculus. And so if I have some curve gamma, and I look at the integral over my closed curve gamma of f of z dz, this equals 0 if there is an f, big F, such that big F prime equals little a. Okay, so this is the nice generalization. And the proof of this is really a multivariable calculus proof of parameterizing the curve. So what you typically do is you have some interval, 0, 1, and you have some map t. So z would be gamma of t, dz would be gamma prime of t, dt, and you would do your parameterization. And so your integral would basically become the integral from 0 to 1 of f of gamma of t, gamma prime of t, dt, and then this would give you big F of gamma of 1 minus big F of gamma of 0. But since gamma of 1 and gamma of 0 are the same, you get, so this would be gamma of 0 equals gamma of 1. So this is essentially what the book is talking about. If we have a primitive, then the integral of our function along a closed curve is 0, because we end up where we started, and it's essentially just the fundamental theorem of calculus. The difference now is we have it over a more interesting shape. The fundamental thing of calculus over a point from on. But now once we have a curve, to say that the integral over this curve is 0, that now has some meat. So this leads naturally to the search for primitives. So I want to know, can you find primitives of functions? If most functions don't have primitives, this is of course going to be a useless result. The hope is that a large class of functions will have primitives. Or maybe you have a function that doesn't have a primitive. And so we can take a function f of z and write f of z as f sub bad plus f sub good. And what do you think might be true about f sub good? Yeah, it has a primitive. And maybe here has well understood issues. And so the idea is we always want to reduce to a simple object that we can study. And so if there's a good part, remove the good part, and then just deal with whatever's left over. So we need to find functions that have primitives. Can anybody give me a candidate? Let's say you make a table. Here is f of z, here's big F of z. What should go on my list? Yes, e to the z. Okay. What's the primitive to e to the z? And why is that the case?
Because derivative.
So what's your definition of e to the z?
I'll just use the theorem.
Okay, so e to the z is the sum, n goes from 0 to infinity of z to the n over n factorial. Okay. So we're going to call this as an aside, and we're going to go on to the next page. And so aside e to the z. And again, this is an extremely important function. It is worth spending a few moments talking about it. What is e to the z times e to the w? E to the z plus w. Why? That's how exponents work. What is 1 over cosine? Secant. Is that right? If you could control the universe, would you have 1 over cosine affiliated with secant? What would you affiliate 1 over cosine with? Cosecant. And what would you affiliate 1 over sine with? Secant. So don't give me this shit that this is how exponents work. These are not yet known to be exponents. What do we have here? We have the sum, n goes from 0 to infinity, z to the n over n factorial times the sum, say m goes from 0 to infinity of w to the m over m factorial versus the sum, let's say k goes from 0 to infinity of z plus w to the k over k factorial. How many of you have seen this before? All right, so if you haven't seen this before, then it's good that we're talking about this now. The fact that we are using the notation of e to the z, what does that make you think? It makes you think that this damn well better be true, or this is bad notation. Sadly, mathematics has been known to have bad notation occasionally. We need to prove this. Why do we need to prove this? Well, if we want to calculate the derivative, the derivative of ez prime would be the limit as h goes to 0 of e to the z plus h. Woo. Would be e to the z plus e to the z plus h minus e to the z over h, which we hope is e to the z limit as h goes to 0, e to the h minus 1 over h. And we hope we can make an argument like that. But to do that, we need to know that the product of the exponentials is the exponential of the sum. So we have to prove this. This must be proven. So I'm not going to bother proving it entirely rigorously. I'm going to just give you a sketch of the proof and you can fill in the details. The first thing is the factorial function grows so rapidly versus polynomial growth that I don't really have to worry about convergence. Everything I do can be justified. And so I strongly urge you to actually justify it. If you have questions, either ask me or ask the TA. Let's rewrite things. When you look at z to the n times w to the m, and you get all the different combinations, I'm going to group them such that the sum of the power of z and w is going to be k. And so this over here is going to be the same as the sum k goes from 0 to infinity, and then the sum L goes from 0 to k, and I will have z to the L. And then what power of w must I have if the sum of the powers is supposed to be k? K minus L. And I'll need people to be quiet in just one moment. Divided by L factorial, K minus L factorial. So if you listen really closely, this expression is screaming at you that it wants something. What does this want? It wants a k factorial, right? This looks so much like a binomial coefficient, which we would get with the z plus w to the k. So let's just multiply by k factorial. Is this legal? No. But if we divide by k factorial as well, then all is okay. And so what would we get? We would get the sum, k goes from 0 to infinity. I can pull out the k factorial, and I'll have a sum, L goes from 0 to k, of k choose L, z to the L, w to the k minus L. Oh, but this over here is just z plus w to the k. I'll put the k factorial down below, and k goes from 0 to infinity, and there's the proof. So this actually proves, as long as you can justify the regrouping of terms, which we know from before is non-trivial. But as long as you put in absolute values, if everything converges, then you can use the Fubini theorem, and everything is going to converge fine here. So this can be justified, but you need to do that if you want to use e to the z. Now that we have that, then we need to justify differentiating term by term. Well, that was the lecture you're supposed to watch beforehand. So justifying differentiating term by term by term differentiation gives ez prime equals e to the z. Talk about Zor at some point. Okay, so now going backwards, we can now include that on the list. So it's a good example. It's on the list now. It was not the example I was expecting to get first. Are you going to be kind to me? What will you give me? Thank you. Right? There we go. Yeah, we know a primitive for 0. We can actually do it a little bit better. What if I give you now 1? Can you give me a primitive for 1? No. Z. You went the wrong direction. So give me the primitive for z. 1/2 z squared, z to the n. 1 over n plus 1, z to the n plus 1. And in fact, any finite polynomial will have just a finite polynomial. So we actually have at least some examples of functions that have primitives. Any finite polynomial things are fine. And there's a lot of things in life that are finite polynomials. Sadly, a lot of things are not finite polynomials. So the question becomes, what if we had an infinite polynomial? What if f of z equals the sum and goes from 0 to infinity of an z to the n, and it converges absolutely in an open set omega? Why do you think we use, yes?
You said we can differentiate like curve by curve, so that we take the like primitive curve.
Okay, so, but that's not differentiating.
Yeah, no, but we can construct a function by taking the primitive by curve.
Okay, so we could do f of z would be the sum, n goes from 0 to infinity. What would we get?
N over n plus 1 and d to the n plus 1.
Good. An, oops, just an over n plus 1, z to the n plus 1. Is it hard to prove that this converges? Why not? It has the same radius of convergence. What makes this a really easy calculation? Well, we don't know. It depends on what the ANs are.
Curve by curve.
Term by term what? I want to know, I know little f of z converges. Why do I know big f of z must converge? No? Just look at the two series. What can you tell me term by term is true about big F versus little f? Yeah, I mean, basically, if you just pull out a z, you play games, pull out z term by term smaller in absolute value. So converge. Yeah, this is the extra n plus 1. Yes? No, pull out a z. Look at the A0 term. Look at the A1 term. Look at the A2 term. And we're dividing by an n plus 1. So if I just match up the A5 term with the A5 over 6 term here, it's got to be better. I don't actually have to use any deep theorems. For differentiation, I have to be more careful. For little f prime of z, that's going to be the sum n goes from 0 to infinity of n an z to the n minus 1. And now you need to use, say, the nth root of n goes to 1. Okay, so it's a little bit more work to prove things term by term, and that's why we actually had to have those arguments to just do things a little bit more carefully. And we need that n to the 1 over n goes to 1. The best way to do that is L'Hopital. Use logs. Whenever you have a product, take logs, and the log of n to the 1 over n is just going to be the log of n over n. Now you L'Hopital. And so, you've made it if your name is a verb. So if you L'Hopital this, you would get the limit as n goes to infinity. The derivative of log of n is 1 over n. Derivative of n is 1. That's just 0. So if you exponentiate, you get 1, which is what was claimed. So n to the 1 over n, the n is getting very, very large, but you're taking such a high root, taking the high root overpowers the n getting large. Think of 2 to the 10, which is 1024, and then take the 1 over 1024th root of 1024, and that's going to be damn close to 1. So it's a little bit of work to prove that f prime of z converges, but it's not too bad. It's actually trivial to prove that if you have a analytic series, if you have a Taylor series that starts at n equals 0, that you can go and just integrate term by term. So that's not going to be a problem at all. So does every function have a primitive? If so, boy, is this class going to be easy. It'll also be boring. For my physics students, where are you? Have you ever taken a class in thermostatics? That's where you hold everything constant. So why have you never taken a class in thermostatics? Yeah, there wouldn't be much to do. If everything is constant in time, the subject is basically done. So if everything integrates to 0, then there's really nothing we can do in complex analysis. We need some functions that will not integrate to 0. Okay, so if we need some functions that won't integrate to 0, and anything that has a primitive integrates to 0, there better be something that has no primitive. So if everything has a primitive, class dismissed. Right, we finished the subject. So can somebody give me a function that doesn't have a primitive, or at least is a candidate for not having a primitive? I'm sorry, great. So candidate for no primitive. And this is f of z equals 1 over z. So let's revisit real analysis. Whenever you're having trouble in complex analysis, try to go back to real analysis and try to build some intuition. If I gave you the function f of x equals 1 over x, do you know any function whose derivative is 1 over x? Log of x. And so, if we're making our table f of x, big F of x, sorry, I don't want big F of x. Let me do it with derivatives. And so what I'm going to want to do is I'll have f of x and I'll have maybe f prime of x. I'm just trying to build some intuition. X squared goes to 2x. X goes to 1. 1 goes to 0. And then 1 over x goes to what? I'm going to take the negative 1 over x squared. And now let's add the antiderivative. So x squared would go to x cubed over 3. X would go to x squared over 2. 1 would go to x. That would be log of x. And if we kept going, 1 over x squared would go to negative 1 over x cubed, negative 2, right? And if we tried to integrate negative 1 over, if we integrated 1 over x squared, we would get negative 1 over x. Right? So look at what we have. We have x, for big F, we have x cubed, x squared, x to the first. Should be x to the 0, then x to the negative 1. So should be x to the 0. Something is going on in the table here. This is the source of all greatness in complex analysis. The fact that we have the logarithm coming here, and there's going to be some interesting stuff happening with a logarithmic function. This is the source for our functions that don't have primitives. So things are going a little bit off when we're looking at the function 1 over x log of x. So that here is the source of what's going to happen. Okay. So any questions about this? Yes.
Any function without
Right, yes. So if your function has a primitive, then that means the primitive is differentiable and is you back. And we're going to learn that once you're differentiable once, you're differentiable infinitely often. So if you actually have a primitive, then that implies that you have to be infinitely differentiable. This seems almost like a backdoor proof. By going up, I can then come back down and keep going.
Without the other way.
What do you mean by the other way? I mean, if I start off with a function that is not primitive, what am I trying to prove? If it's primitive, then the function is holomorphic. And so then the question is, if it's holomorphic, does it have to have a primitive? And so the answer, I believe, should be yes. That if you are holomorphic, in the whole region, then you should have a primitive. And in fact, we will prove that in a little bit. Okay. And in fact, we'll even come up with a specific way to construct that. So the function 1 over z is going to be our most interesting example throughout the whole class. All right. So we had a discussion earlier about the 3 great shapes of mathematics. Right? What are our candidates? Rectangles, triangles, and circles. It is not easy to combine circles. Every now and then you get some legislatures who tried to stick their heads and necks into places they should not. There was one that decreed that pi should equal 3, exactly. And thank God, before it was finally passed, somebody who happened to be in town who was a mathematician, and one of the legislature members, showed this to him, and he goes, "Oh dear God." He quickly went to the session and said, "You guys can't do this." Sometimes things are snuck in because nobody actually looks at what's being discussed, such as the person who made a motion to have a day in honor of an axe murderer. Just curious to see if anybody was looking. So pi was almost declared to be 3 in one of the states of our nation. What would you do if pi was declared to be 3? I would, do you buy land in circles and sell in squares, or do you buy land in squares and sell in circles? You can take advantage of the exchange rate. All right, so I'll leave that as an exercise to you as to how you could exploit something like that. So we will do Goursat's theorem. So this is the first of our really big theorems. So we've done integration along curves. We're going to use triangles for Goursat's theorem. And then what I want to do is I want to have a statement in the books. We're going to have an open omega. T will be a triangle in omega. F is holomorphic in omega. Then the integral over the triangle of f of z dz equals 0. Okay. So this is our first big theorem. So as long as I give you a holomorphic function and I integrate over a triangle, it's going to be 0. So I'm going to sketch the proof. So the idea is I start off with a triangle. Okay. And now what I'm going to do is I'm going to divide each side in half. And hopefully this picture looks pretty good. And we will now have 4 triangles. And we have to always think of what name do we want to give them. And I will call this T sub 1 with a superscript 1. I'm trying to use the same notation. T sub 2 with a superscript 1. T sub 3 with a superscript 1. And in the Shaka, T sub 4 with a superscript 1. And the initial one was T sub 1, I guess, with a 0. There was just one triangle. Okay. What can you say about these 4 triangles? What interesting properties do they have? Yes. They're similar. So if this angle here is alpha, because we have the red line is parallel to the base, this is also going to be alpha. If this is beta, this is also going to be beta. Okay. And if we call this angle up here gamma, we clearly have now a couple of similar triangles. So the first question is this red line, is this red line coming down like this? Is that parallel to the other side? So how would you prove something like that? So do we know that those lines are parallel? I'm doing it by midpoint. So is that enough to prove that that line is parallel to the other line? Right. So in fact, I'm asserting that that line is, that those 2 points are at the same height. But of course, since I'm going halfway down, the same height is not a problem. So with a little bit of work, you can show that these lines are parallel. So the question is just what is the best way? If I start, if clearly the vertical line here is the same as the vertical line here, and then if I do the same argument, this is halfway over here, and these points are halfway over here. If I look at these triangles, I have beta, gamma, alpha, and so I just need to have one more angle to be the same, and then all 3 angles will be the same. And so this down here is going to be parallel to the line over here just by a very similar argument. And so,
When you say down here.
oh, sorry, it doesn't show it. Sorry. Let's call it, A, B, C, D, E, F. So EF is parallel to AB, and then similarly, ED is parallel to CB. Because we're cutting them in half, and so by playing some games corresponding parts of congruent triangles, you'll have like angles, side angles, stuff like that. You can see that this is going to have to be gamma over here, so this has to be beta, and you can keep playing these games. So it's a nice exercise. Prove similar triangles. Okay. And what can you tell me about the triangles? Well, each one is going to be smaller than the previous. And in fact, each one of them is going to be, the sides are going to be 1/2 the original. So sides are 1/2 the previous level. So for instance, being a little bit vague, the diameter of any Tn plus 1k would be 1/2 the diameter of a Tnj. As we go down a level, things are getting closer. Yes.
What is diameter?
I'm being a little bit vague. Say the largest separation between points on the triangle, the length of the largest side, something like that. Just some measure of its length. How do you think area would change? Would be 1/4. So area would be 1/4. Because area is going to be product of lengths. So if we have something like this, then oh yes, I have to shift. I have to switch this to the switch and subswitch. Thank you. So what I want. Thank you. So this should be level n plus 1 to level n, choosing anything down here versus anything down there. Thank you. All right, so why is this useful? Well, if we try to do any of the integrations, if I give you some triangle to integrate over, and I break it up into triangles like this, and I start to do the integration, this is what I have if I integrate over the original outer triangle. But I can move and I can integrate over the inner triangle as long as I go in both directions. Because if I go in both directions, then it cancels out. This should look very similar to Green's theorem. I've just added integrating over the 3 internal segments. And because each one of them is traveled in both directions, they cancel out. So the integral over the whole triangle is equal to the integral over the 4 triangles. So integral over the whole triangle at some level is equal to the integral over the 4 triangles at level Tn plus 1. Okay. And so if that's the case, then for at least one triangle, we have to have the following. We would have the integral over, say, one of our triangles at level Tn of f dz would have to be less than equal to 4 times the integral over one of our triangles at level n plus 1. So why would something like that have to be true? Yes.
That one indicates the
Right, it would be less than our original triangle. We know that the original triangle is equal to the sum of the four things. And so if it was greater than 4 times that, then if there was no cancellation, if we know, for instance, alpha equals a plus b plus c plus d, if alpha is greater than the max of the absolute value of a, absolute value of d, we're in trouble. Because this side here is less than or equal to 4 times the max of the absolute value of a through d. You just assume that there's absolutely no cancellation. So if there was no cancellation, then you would just add everything. So the worst case is to have all of them of the same phase and the same magnitude. And so we know that there has to be at least one triangle whose integral is at least 1/4 of the triangle we started with. And we can just keep iterating this down. Okay. So the idea is we want to constantly reduce to smaller and smaller triangles. Because on smaller and smaller triangles, then we're going to have very little variation in the function. If the triangle becomes extremely small, what is our function going to look like? Constant. So goal is to reduce to small triangles where f is approximately constant. Okay, so as we continue,
Sorry, I'm just not sure I understand like what that leap was.
I'm sorry.
I'm not sure I understand how you got from as you get to small triangles.
Well, just because the triangle is getting smaller and smaller and smaller, so z can't move that much. If I stay on a very small triangle, then as I move z, f of z can't really move that much because z isn't moving that much. Any function that's holomorphic, that means the function is differentiable, so it can't change that much as I move z a little bit. I'm just localizing like that. And so what we get is that as we expand things out, we keep doing this, and we keep doing this, and we keep doing this. So we get the absolute value of the integral over, say, Tn of f dz would be less than or equal to 4 to the n times the absolute value of the integral of, I'm sorry, this should be the original triangle T0 and one of our triangles Tn f dz. And so we started off here. Maybe this was the triangle, and we divided it again, then this was the one, and then this was the one. And at some point, you can no longer see the triangles I'm drawing. We're just zooming in on it like one little point into here. And so now let's try to figure out what is going on when we're on that small triangle. Well, f is holomorphic. So what does that mean? It means the limit as h goes to 0 of f of z plus h minus f of z over h equals f prime of z. So f of z plus h would be f of z plus f prime of z, z minus h, plus I'll call it e of zh. And this goes to 0 as h goes to 0. And in fact, it goes to 0 even when I multiply, I believe, by z minus h. Yes. So that's what it means for the limit, is that as h gets very, very small, f of z plus h minus f of z over h gets very close to f prime of z. How close? It's missing by something, I'll call it error function of z and h. And the error of z and h is so small that it has to be tending to 0. Okay? So again, we just have f of z plus h minus f of z over h is equal to f prime of z plus e zh. And I'm not really saying anything about that function. I'm just saying, look, it's not exactly f prime of z if h is not 0. And again, we're never taking h to actually be 0 in the limit. We're just looking at what happens as h gets smaller and smaller and smaller. As h gets smaller and smaller and smaller, this ratio is getting closer and closer to f prime of z. How much does it miss by? Let's just call it error. I can call it whatever I want. And what must be true about this error? It must be that as h goes to 0, this has to go to 0. So the limit of this, limit as h goes to 0, must be 0. And now I'm just multiplying through by h, and that's just how I'm getting the previous line. So all that is going on here is that, we're saying because the function is holomorphic, we can write any f of z plus h as f of z plus f prime of z, my instantaneous speed, times z naught I've moved, plus a little bit. Okay? Now, instead of z and z plus h, we can use z naught and z. And then we would get f of z would be f of z naught plus f prime of z naught, z minus z naught, plus error of z, z naught times z minus z naught. Okay, when we look at this, do any of the functions here have primitives? So what has a primitive? Yes.
The first two.
Yeah. What's the primitive?
Z times
Is z times f of z naught. What's the primitive?
times Z naught times Z minus Z naught squared.
F prime of z naught, z minus z naught squared over 2. Not necessarily possessing a primitive. But we know it's small. And so when we try to figure out what is going on, for the integral over one of these small triangles, here's one of our triangles at the nth level. And we're doing the integral over this triangle Tn of f of z dz. Well, what's the contribution from the f of z naught? That's just 0. What's the contribution of the z minus z naught term? Also 0. And now we're left with the integral over the triangle of the error function z naught, z minus z naught dz. And we want to get a sense of how small is this going to be. Okay. All right, well, we've got a z minus z naught, so we can try to estimate this. All right, and so if we want to estimate, it's going to be, in absolute values, is going to be less than or equal to the maximum of E of z naught, an absolute value, times the length of Tn times the maximum value of z minus z naught. So do we agree that if I want to estimate the integral, worst case, take the largest value of the error function, take the length of the triangle, and take the largest value of z minus z naught? Or just what I'm integrating over. Yeah, the perimeter. Length of perimeter. And I'm explaining things about z naught. Z naught is some point inside here. I know because my triangles are nested that they have to converge to something. This is why I wanted you to watch the video beforehand so I could try to just emphasize the key points. There's a lot going on here. Well, what's true about the length of Tn? We know that it's getting smaller. This is going to be, less than or equal to 1/2 to the n, the length of the original triangle. And then the max is going to be less than or equal to 1/2 to the n, like the diameter of the original triangle, because each one is getting smaller and smaller and smaller. And this, what do we know about this term? Goes to 0. So we get something like constant times 4 to the n times something going to 0. I'm sorry, 4 to the minus n. All right, well, this is really good. Because if you looked at what we had before, we said that this is going, the integral over Tn is going to be less than equal to 4 times the integral over the next level. So the factors of 4 to the n and 4 to the minus n are going to perfectly cancel. And when you put all the pieces together, you get the integral over the original triangle of f of z dz is going to be less than equal to 4 to the n times 4 to the negative n times something going to 0. Therefore, it is 0. So this is Goursat's there. And the idea is we just keep checking the string, the sequence of triangles. Yes.
So if we did send the big triangle, what would go wrong with the error term of calculation?
Yeah, the error term just wouldn't go to 0. And so if we're just integrating over the big triangle, where's the big triangle? So if we integrate over the big triangle, we don't really have a good way to use the differentiability. Differentiability is a local concept. And this is going back to the tangent line approximation, the tangent plane approximation. Locally, we're a point. And if you look at what happens when we Taylor expand things, well, we don't quite have a Taylor series. We have the beginning of a Taylor series. Because you're holomorphic, we start off like this, plus a little bit of an error. And that z minus z naught that's present there is going to still be small. And so that's going to give us this little extra bit that we need. If the function was differentiable, what could you tell me about this error? It would be at least how small? Maybe at most how small. I'm not sure how you do it much. If the function was differentiable, what could you tell me about the size of the error? It would have to be z minus z naught. Because the next term would be a z minus z naught squared. So if my function was differentiable, the next piece should be something like a z minus z naught squared. So I would expect this term, not only is it going to 0, it's going to 0 at least as fast as z minus z naught. Maybe I've decided to be evil or nice and give you the sine function. The sine function only has every other term. It's x then minus x cubed over 3 factorial. There is no x squared term, or there is, but it has a coefficient of 0. So if you were to try to do the Taylor series expansion of sine, you would actually have extra cancellation. It wouldn't be a z minus z naught squared term next, it would be a z minus z naught cubed term. That's okay. I'm just saying that the error is no worse than a z minus z naught. And that's essentially what's going on here. All right, so this is a good place to stop. I am happy to stick around in case anybody has